Hi, my name is Joe Moore, and I'm from the Johns Hopkins University Applied Physics Lab. And I'm here to present our paper, Design and Analysis of a Fixed-Wing Unmanned Aerial-Aquatic Vehicle. This is a joint work with Andrew Fein and Will Setzler. So there's been a lot of work done to design unmanned underwater vehicles as well as unmanned air vehicles. But there's been relatively little work done to design unmanned aerial-aquatic vehicles. And yet we think that there's a great potential in enabling a lot of new mission capabilities with these multi-domain unmanned aerial-aquatic vehicles. For instance, if you wanted to sparsely search a large body of water, you could do so very quickly with a vehicle that could gather information in the water and then fly very long distances to a next sample site. In addition, if you wanted to fly into a landlocked body of water, you could do so at a long range and then gather information and take that information out again. There's been a number of exciting works in this area recently that have sought to develop unmanned aerial-aquatic vehicles. There have been works that have sought to develop systems that can take off from the surface of the water or from underneath the water surface. There have been systems that have been designed to dive into the water and locomote but not come back out again. And then there have been systems that have attempted to design systems that can both swim and fly and transition back and forth between the two different domains. And that's one of the areas that we're targeting in this work. So when we were beginning our design analysis, we made some observations about one of nature's most advanced aerial aquatic systems, the flying fish. And what we noticed is that the flying fish actually puts energy in during the water-to-air transition. Normally we think of them as building up momentum and going into a straight glide, but a lot of times they actually use their tail to thrust through the water. And this starts to look like some of our aerobatic maneuvers that were done in John Howe's lab at MIT a few years ago, where you go from a prop hang configuration to a forward flight and back again. And so maybe there's something to learn about these aerobatic maneuvers and how they apply to unmanned aerial aquatic vehicles. In addition, these systems are doing feedback across the multiple domains. And we have examples of this in the robotics literature in walking robots, where multi-domain systems do feedback through different mode transitions. And so our goal is to be able to design a system that relies on automatic control and a simple airframe design to enable multi-domain locomotion through intelligent control. And as I said, we want to design an airframe that's very simple, but we want to make sure that our airframe is feasible, that it can execute a water-to-air transition and back again. And so the first thing we looked at was what kind of propulsion mechanism we would use. There were three sort of in the literature that we noticed: rocket propulsion, flapping wing flight, and propeller propulsion. And when you look at an air propeller and a water propeller next to one another, they don't look a whole lot similar. But what you notice is that an air propeller can actually be used in water. If you look at the Reynolds number scaling, if you're willing to slow the propeller down about 14 times, you get about 4 times the force in water that you would in air. And what's also interesting is that if you're willing to slow down the vehicles, the wing, by 14 times, you get equivalent propulsive efficiency, motor energetics aside, in the water as you do in air. And we actually looked at this. We put air propeller in water, and we were able to show that we were able to get similar comparable thrust characteristics in water that we got in air. So this means that we can use propeller propulsion to actually locomote through water and then into forward flight. As far as airframes go, if you look at sort of seabirds, what you'll notice is that they often dive into the water with swept-back wings. This is to limit their cross-sectional area. And we actually have examples of systems that have airplanes that actually have reduced cross-sectional areas without having swing wings, these delta-wing vehicles. And so we decided to model our system as a delta-wing aircraft to reduce the amount of forces upon entry. And then, so we also looked at this water exit maneuver, and we looked at simplified dynamics to see what kind of forces would be required to exit the water. And what we found from our simplified analysis was that if you're willing to have a positively buoyant fuselage, you actually get a nice buoyancy assist when you come out of the water. And for our system, which only has a 5 Newton thrust capability, we actually got 1.8 Newtons extra thrust from accelerating through the transition. And what's also nice is that we can get the most buoyancy assist per area by using this triangular planform. But this is a very simplified model, and before we decided to actually fabricate our system, we built a more sophisticated physics model. This is your typical aerodynamic model, but we add in hydrodynamic forces as well as the added mass. And we also look at span-wise circulation to calculate our aero-hydrodynamic forces. And this is important because it allows us to decompose the wing into the components that are above and below the surface of the water and compute each of the aero and hydrodynamic forces separately. After that, we actually developed a hydrodynamic model based off of this physics model, where you have 4 different modes: water to air, air to water, and water and air. And then we did trajectory optimization across those different domains, so we can specify a goal condition and a final state. And then we can design a trajectory that crosses through all domains. And what we were able to find is that with our 5 Newton thrust limitation on this particular design, we were able to exit into a steady level flight condition. So here's a video of our hybrid trajectory optimization and optimal trajectory execution. So the next thing we did was we designed our vehicle. We built our vehicle. It consists of a carbon fiber fuselage with a foam core, a standard 18-amp waterproof speed controller that we waterproofed, a 2300 kV brushless motor, 6x4 propeller, battery, and a 72 megahertz receiver for doing hand-piloted control. And then we tested our vehicle. We took it out to fly to make sure that we hadn't designed our system to be too heavy. We wanted to make sure that we could get good, stable flight, and this is all hand-piloted. So you can see the system flying at about 30 miles an hour with good performance. And then what we did is we took it out to someone's pool in their backyard and we threw it in. And we wanted to see how tight of a turn it could do. And we were quite pleased with the maneuverability of the vehicle. We can see it do a nice tight turn around the back of the pool here. It's going about 1 mile an hour here. And finally, we really wanted to see if we could do the transition. So we had the best pilot we could find try and do a water-to-air transition for us. And we shut it off before we could fly into the guy's house whose pool we were testing in. So this is really exciting, but it doesn't really answer whether or not we can do this successfully autonomously, which is what we would have to do if we actually wanted to realize this system. So what we propose doing is actually using the propeller not only as propulsion, but as a domain transition sensor. And if you look at this plot here, it shows the RPMs through a transition. So we started about 500 RPMs, and then we immediately transition to 6,500 RPMs as soon as we go through that transition. In about a quarter of a second, we're able to ramp up from 0 to 17,000 RPMs for this system. And it actually functions as a nice domain transition on the front end. And on the back end, we use a pressure sensor to sense when our tail is out of the water. And so here are some late-breaking results that I want to share with you guys. Basically, we were able to do trajectory following with this vehicle. In addition, we have a multi-domain state estimator estimating the state of the vehicle. And here's one of our first videos of doing closed-loop control through the transition. So the vehicle's diving, following a trajectory, approaching the surface. And this is fully autonomous. And here's a plot of some of the data. You can see the nice step transition between the three different modes: water, air to water, and then air, as well as the plot of the pitch as the vehicle comes out of the water, and the depth. And what's interesting is that we're actually able to measure speed using the speed of the propeller pretty accurately underwater, which is nice. And then we can actually do dead reckoning between the transition from water to air for about a good couple of seconds until we achieve stable flight, and we get our GPS lock. So I wanted to thank the people at APL that I have had great conversations with, as well as the folks whose pools that we've used during these experiments. Any questions?
Thank you very much. Are there any questions to the author?
Thank you. how the robot navigates when flying or swimming?
Say again?
How to navigate in flying or
Yeah, so we have an IMU on board, and we have a depth sensor, but we're not doing any sort of lateral or longitudinal positioning of the vehicle underwater. In the air, you would use GPS. Yep.
There was another question.
How do you handle the control right around the hybrid mode switch? Are you doing a transverse LQR? And if you're doing trajectory time tracking, like TV LQR, what if you're a little late approaching your transition?
Fantastic question, yeah. So we're not doing transverse LQR, unfortunately, though that's part of our future objective. But we are doing time invariant LQR at the end of each mode. So that drives us into a trim condition that takes us across those modes. So if we're a little late, then we use that to get across the threshold.
Any final questions? Okay, one final question.
About how large of a vehicle do you think you could scale this to? Like how big?
Yeah, that's a good question. So we did look at that. If you're willing to scale up to 1 meter, you can have a payload of about 1 pound. So it's a pretty significant jump. Right now, we really have no payload margin. After you get to 1 meter, it starts to be parasitic because the weight of the motor actually starts to affect you, the electric motor's weight.
Thanks.
So.
Great, thanks a lot. So let's thank the speaker one more time.